Hi class, this is Dr. Martino. This is full lecture number 2 for the respiratory system. This is the slide we ended at. Just to reiterate what we did last time as a reminder, we talked about the sequence of events for breathing. You need to memorize those. Boyle's law and how it applies to the respiratory system. We talked about the different connection points, the chest wall, the intrapleural space, the lung, the properties of the lung, and the properties of the chest wall, where the lung wants to collapse and the chest wall wants to expand, and that they come to a balance point, that the chest wall, through the connection through the intrapleural pressure, PIP, keeps the lung from collapsing, and that in order to get a breath in, the main pressure that causes that is a negative alveolar pressure, and it is always has to be negative in order to take in a breath, and that means that transpulmonary, which is always positive, has to increase. And remember, the intrapleural pressure is always negative. So intrapleural pressure is negative. It becomes more negative when you take in a breath. Transpulmonary pressure is positive. It becomes more positive when you take in a breath. And alveolar pressure, when you're not taking a breath, is 0. And in order to take in a breath, becomes negative. We also talked about some of the muscles and how the diaphragm muscle works, and the airways, which you need to memorize, and some other factors. So let's get back to this. So in the next few minutes, hopefully I can explain to you how to use this diagram as a tool to understand the respiratory control system. You have 3 curves, right? You have 3 curves. On the y-axis, you have pressure for these 2 curves and volume change for this curve. On the x-axis, you have 2 blocks or columns. You have an inspiratory block or column and an expiratory block or column. Pressure is always measured in centimeters of water pressure in the respiratory system, and the volume change in this case is liters. So let us begin at this point here. So at this point here, these are all related. There is no movement of air. There is no movement of air. So if you draw a line from this curve straight across to the left, you see that there is 0 pressure. Atmospheric, remember, represents 0 pressure all the time. And if the alveolar pressure is 0, then there's no gradient. Then there's no gradient for you to move air. At the same time that the alveolar pressure is 0 at this point, there is 0 volume change. 0 volume change. Now there is always residual air in the lungs. Most of the time when we take a normal tidal volume, a normal resting breath, there is always air left in the lungs that is not residual, and then there's this residual air. Okay, we'll talk about that more later. So then we look at pleural pressure, and pleural pressure is about -5. Okay, pleural pressure is about -5. So what happens? We start to take in a breath, right? So pleural pressure starts to change. Now notice how steep this curve is. And it has to be steep because you have to begin to overcome the elastic properties of the lung, of the alveoli. So you're going to apply more pressure than what you're going to get out here. So by the time you get to this point here, right, to this point here, which is halfway through an inspiration, give or take, maybe a third, what has happened is the pressure has dropped from 0 to about -1. Well, you draw a line straight up, or straight as you can be, and you see that you're roughly at about 0.25 liters of air that you've taken in. Then you take a look by going straight down, straight as you can be, what the change has been in pleural pressure. Well, pleural pressure started at -4, right, and is now at about -7. So clearly there's been a 3 centimeter of water drop in pleural pressure, but there's only been a 1 centimeter of water drop in alveolar pressure. Again, you have to overcome the elastic recoil of the lung. You continue on your breath, right? You continue on your breath and air has been moving in. And what starts to happen is that pressure in the alveoli start to come up, but it's still negative, right? It's still negative until you get to the end of inspiration. And at this point, you're back to 0. But during this whole time, you go from 0 to -1 back up to 0. As long as this value is negative, air is coming in, and that is true, right? Because in this portion of the curve, an inspiration, you have the other 0.25 liters of change in volume. And this is significant because an average tidal volume, and that's what this is, tidal volume. So tidal volume, T stands for tidal, V stands for volume, for an average human being is roughly about half a liter. Okay, so we get to the end of an inspiration. And you've taken in 0.5 liters of air. You went from 0 alveolar pressure down to -1, back to 0, and you started, right? You started your pleural pressure at about -4. Oops, I made a mistake here. This should have been -5. Sorry about that. I said it was 3. So -5, and you go down to about -7. Okay, -7, and then by the time you're all done, you're almost at about a -8. Okay, so you get to the end of an inspiration, you have a half a liter of air in your lungs, you have 0 alveolar pressure. That means alveolar pressure and atmospheric are the same, so that means no air is moving. And your pleural pressure, which is normally at -5, has gone down to about -8. Now the air is being held in the lungs because the diaphragm is still contracted, and pleural pressure has to be negative. So now what happens? At this point, you release the diaphragm, and expiration is a passive event. So this is active, right? You need to use energy to do this because of the diaphragm in inspiration. And this part here is passive, right? It is passive. So the recoil of the lungs, remember the lungs are like a rubber band, and when you stretch them, they recoil, meaning they go back to their original shape. So you release the diaphragm and air starts to leave the lungs. And as this is happening, right, in order for this to happen, what has to happen is that pleural pressure has to start to increase, which then drives up your alveolar pressure. And remember that air can only move out of the lungs if the pressure in the lungs is greater than atmospheric, and atmospheric is always zero, so anything greater than zero will cause air to flow. You get to about a third of the way through expiration, and you can see that you've come down almost 0.25 liters, and then the other 2/3 of the expiration, you see that pleural pressure continues to increase back to -5 centimeters of water, and alveolar pressure goes up to about +1 and eventually comes back down to 0. And then you're back at whatever the resting amount of air is in the lung. Remember, this is volume change, not the actual volume. So hopefully this diagram shows you all of the events that occur in this sequence, right? Inspiration, expiration, but shows you in a more mathematical format. There are 3 points where there are 3 points where there's zero alveolar pressure, and that becomes important at the beginning of an inspiration, at the end of an inspiration, beginning of expiration, and at the end of expiration. That becomes important as we move forward. Now, what we didn't talk about in this whole thing is just transpulmonary pressure thing. Remember, transpulmonary pressure is always positive. Pleural pressure is always negative. Transpulmonary pressure is always positive. And alveolar pressure is either 0 if there's no air moving, negative if air is moving into the lungs, and positive if air is moving out of the lungs. And transpulmonary pressure is the relationship between alveolar pressure and pleural pressure. So we're going to show this to you mathematically. Let's move on to this, and then we'll talk about the mathematics in a few minutes here. This is an esophageal balloon. It is a piece of equipment that you can insert into the esophagus of an animal, including a human, and inflate it. And it can give you the ability to measure different kinds of pressures, right? Different kinds of pressures, because this is the trachea and this is the esophagus. And the esophagus and the esophageal balloon is down here. When you inflate the esophageal balloon, because of the approximation to the trachea and the bronchi, and because you can insert the esophageal balloon down to the esophagus at the level that is mid-lung, right, about mid-lung, you can start to understand some of the pressures that occur in the lung. So in this example, in this diagram, we're going to say that airway opening pressure is 760 millimeters of mercury. That's just atmospheric. Elastic recoil of the chest wall is the pleural pressure minus the surface of the chest, right? So the pleural pressure minus the chest. So the pressure that is in here minus the pressure that is out here. So that equals the elastic recoil. Of the chest wall. The elastic recoil of the lung is the alveolar pressure minus the pleural pressure, right? So it's Alveolar pressure in this case is the same as atmospheric when no air is moving. And pleural pressure, as we saw in the last diagram, is about 5 millimeters of mercury less than atmospheric, right? 5 less. Okay. All right. So let's move on. So this is a device, an esophageal balloon, that allows you to measure some of these pressures. Another important graph that starts to get at more of these equations that start to help you to understand this graph is in this slide. So this slide is titled Calculating Transpulmonary Pressure from Pleural Pressure. From pleural pressure, doing what's called a breath hold maneuver. It's important to memorize these equations. So transpulmonary pressure is alveolar pressure minus pleural. So it's the alveolar pressure minus the pleural pressure, right? So the transpulmonary pressure equals P alveolar minus P intrapleural. Now we're going to go back. We're going to go back here, and we're eventually going to understand what this all means using these equations. So it's the alveolar pressure, right? It's the alveolar pressure minus the pleural. So in this case, if P alveolar minus P pleural equals transpulmonary. So at the 0 point here at the beginning, alveolar is 0 minus -5. Then transpulmonary pressure is 5 centimeters of water. At this point here, alveolar pressure is -1, and intrapleural pressure is about -7. That means that transpulmonary pressure is 6 centimeters of water. The bottom here, at the end of the inspiration, alveolar pressure is 0 minus roughly 8. My eyes are not very good. We're just going to call it -8. Right? That's going to be about 8 centimeters of water. This might actually be 7. It's hard for me to see with the graph the way it's written, so that might just be my eyes. It doesn't matter. Here's the trends, right? There's no airflow here. No airflow here. Alveolar pressure is 0. You have pleural pressure, which is negative, and transpulmonary is positive. You have inspiration here. Inspiration here, alveolar pressure is negative. Intrapleural pressure becomes more negative, and transpulmonary goes up. Gets bigger, more positive. The end of inspiration, and inspiration, alveolar is 0. There's no air movement. Pleural pressure has gone down even more, has decreased, become more negative. And transpulmonary pressure is the greatest. Now, there's a couple of things you'll notice. When there is no flow, pleural pressure and transpulmonary pressure equal and opposite, right? This is -5, this is 5. There's no flow at the beginning of inspiration. At the end of inspiration, this is -8, and this is +8. So you can start to see some relationships. Okay, so that's this equation. You measure pleural pressure, which is all big P subscript PL is the same as big P subscript IP. So you measure pleural pressure at rest and at the end of max. So on this graph, the 0 is here and the 0 is here at the beginning of inspiration, and the end of inspiration, the beginning of expiration and the end of expiration. There's no air moving. There's no air moving. So at this point and at this point, alveolar pressure must be 0. And when we did this just now, right, there's no air moving here, and there's no air moving here, alveolar pressure must be 0. But pleural pressure, remember, pleural pressure was -5, and transpulmonary pressure at this point was, so this was -5 for pleural pressure, +5 for transpulmonary. At this point here, pleural pressure was -8 and transpulmonary was 8. So at 0 flow, transpulmonary is equal and opposite to pleural. That is always going to be true. This is one of the compliance curves. There's several compliance curves that we talk about in respiratory physiology. This part of the compliance curve represents inspiration and the changes. This part of the compliance curve represents expiration. The easiest places to figure out pleural pressure would be at the 0 points, right? At the 0 points, because transpulmonary pressure equals alveolar pressure minus pleural pressure, right? So if we want to isolate this, right, you can subtract. That means a transpulmonary pressure minus alveolar pressure equals a negative pleural pressure. Right? So equals a negative pleural pressure. And we can multiply a negative through both sides. And that means that a negative transpulmonary pressure plus P alveolar equals a positive pleural pressure. It doesn't matter what format you keep this in, you're going to get an answer that you can use. Don't get too caught up in the math right now. I'm not so concerned about the math. So because there is an interface, in this graph is the lung change in volume in liters versus pleural pressure. Because there is an interface between air inside the lungs and water in the pleural space, you see this hysteresis. This is what it's called, hysteresis. All right, and so you're going to use more energy because you got to overcome surface tension, and of course, you've got to overcome surface tension, but you also have to, you're overcoming the elastic recoil of the lung, right? And this property, this graph that we see here, if we were to take a look at the properties of a rubber band, this looks like the properties of a rubber band. So that's the important part, right? Or else this would be just a straight line up and a straight line down, and it is not. So what's the important point of this slide? There's a couple of take-home messages. One, you need to memorize transpulmonary pressure equals P alveolar minus P pleural. Two, you need to remember that at the 0 points when no air is moving, that the alveolar pressure is 0. Three, this is a compliance curve, and then the reason that you're getting this outward movement here and this outward movement here is because of the recoil effects of the lung and this thing called hysteresis. So with a breath hold maneuver, you have somebody, basically what that means, somebody or an animal, take in a deep breath and then hold. Okay, we know that at 0 flow, transpulmonary equals negative pleural pressure, right? Because transpulmonary is always positive and pleural pressure is always negative, and they're equal and opposite. So if this is 5, this is going to be negative 5. And we showed that when we looked at the other diagram. You connect 2 points, right, where you began to where you end. You assume 0 flow along the line, along this line, 0 flow, and you can estimate transpulmonary at any given pressure. So at 0 flow here, pleural pressure, let's say, is about -6. While transpulmonary at that point, has to be equal and opposite. So if the pleural pressure is -6, we can then assume that the transpulmonary at this point must be equal to 6 centimeters of water. You do the same thing on the end of expiration at this point. If we can say that -4 is the pleural pressure, then at this point, transpulmonary pressure must be 4. And again, this goes back to this diagram here where we showed this to be true. This is challenging. These concepts are concepts you're going to need to struggle with. They don't come intuitively. You're going to have to go through all of the lectures, and then we're going to have to spend time doing some exercises sort of to get this point across. It's not easy. Don't feel frustrated. It's challenging. We'll get through it. So, calculating alveolar pressure. If you measure the pleural pressure using that balloon, right, and that balloon, this balloon allows you to measure pleural pressure. So the pressure in here and the pressure in here are going to be the same. And so because of that, if this is a -5, then what you will be measuring at this balloon will also be a -5. And that's the curved line, right? It's the curved line here in inspiration. And this allows making this curved, this compliance curve, because compliance is volume over pressure, and we haven't really talked about compliance yet. Then you can calculate alveolar pressure. So what do? You take in a breath, right, and you hold it. This is the 0 point. At this point, the pleural pressure is -6, right? -6. We also know that the transpulmonary pressure must be equal and opposite, so that it must be 6, right? So if you rearrange the equation and you say that transpulmonary pressure is 6 plus a -6 for pleural pressure, then you get that alveolar pressure must be 0, and in fact it is. So you could do the exact same thing here at the beginning. At the beginning of a breath, you can say that your pleural pressure is -4. Because you're not moving any air, that must mean that transpulmonary pressure is equal and opposite is 4. And then you can calculate alveolar pressure at being 0. Now, what is lung compliance? We've mentioned that several times. Compliance, we talked about this when we were talking about the heart. Compliance is volume over pressure. In this case, it happens to be the change in lung volume over pleural pressure. It's the stretchability. It's how easily something is stretched. It's different from elasticity, right? Elasticity, or the recoil, is the ability of an object when deformed to come back to its original shape. Okay, that's all it is. The recoil, the elasticity. The compliance is how easily you can stretch. So if you've ever had this experience where you have two rubber bands, one's a thick rubber band, one's a thin rubber band, the thick rubber band is much less compliant. It is much more challenging to open it, and it also has a greater recoil. The thinner rubber band has a high compliance, high stretchability, and its recoil, its ability to go back to its original shape, is not as great. So compliance is the change in volume over the change in pressure. In this case, it's transpulmonary pressure that we're going to use, which is the slope of the dotted line. The slope of the dotted line is transpulmonary. We use a breath hold. Remember that it's an estimation of compliance. It's actually not linear. This graph, if you actually drew it out, if you saw some of the more advanced versions of this, the actual curve looks like this. So that straight dotted line ends up being a curved line. But for this level of fizz, it's fine to just estimate it as a straight line. Here is another set of compliance curves. This one is important for thinking about movement of air in and out of the lungs under different conditions. I think I want to stop here because that was just a lot of information. It's a lot of conceptual information, and it's important that you go back, maybe listen to this again, and try to come up with questions or try to figure out what you don't actually understand before we get into the next one. Hopefully that was useful. Hopefully that was understandable. Again, don't be so worried about the simple equations right now, although you will have to be able to do them. But think about conceptually, do you understand the mechanics of the lung that we have just described? All right, take care.